Okay, so I know this is a little odd, but here we are. I wanted to talk to you about the lab that we did last week, and we investigated current versus voltage through a resistor. The main point is to find the relationship between current and voltage. We did not change the resistor, so we left that constant. That's going to be one of the underlying assumptions. And this is how we set up the circuit, and you can use this actually as your apparatus. You had the direct current, the DC power supply, which substitutes for the battery. You remember we went from 0 and then we went up to 6 volts in 1.5 volt increments. We are going to use Benjamin Franklin's conventional current. So we'll say that it's the positive charges that flow in that direction. Okay, now in full well, that's not true, but whatever. I realize there's a glare over here, but whatever. Okay, so we set this up, and I just want to say something about how a charge flows in a direct current circuit, one that has a battery. Remember, this is the negative terminal. I'll use a different color. So here's the negative terminal. And we can say that that is at 0 volts. 0 volts. And then here is the positive terminal. And let's just use a number, say 3 volts. I know it anywhere from 0 up to 6. That was the selector switch. So be a charge. Get charged. Be a charge. You're an electrical charge. You're a positive charge. Pretend like you're flowing through the circuit. This is like the ground floor of a water slide. So you're on the ground floor. You take the elevator up. It's a fancy water slide. You take the elevator up, so it gives you potential. That's what the battery does. It gives you potential. You make your way over. You're on like the 3rd floor, if you will. You make your way over along the walkway, and then you go. So right here, assuming there's no potential lost up here, you're still at 3 volts. And then you go down the water slide. Okay, it's not a perfect analogy, but just go with it. So you go down the water slide. Whee! So the voltmeter is measuring your potential here, and now you're back down on the ground floor, 0 volts. You make your way along the ground floor, get back in line, then you get on the elevator, go up, gain your potential. You're on the 3rd floor, go over here, go down the water slide, you're back on the ground floor. You can do this all day until somebody shuts it off. Well, chargers are at the electrical circuit amusement park. The battery gives them potential. They use up that potential. The battery gives them potential. They use up that potential over the resistor. The battery gives them potential. They use it up and keeps on going in this loop. What is the EMF? Well, you know that your battery, like any battery that you put in a calculator or a flashlight or whatever, has a printed voltage on it. Well, that means that there is a potential difference between the 2 terminals. But you only get 3 volts out of a 3 volt battery if you don't use it. There's nothing wrong with your battery, it's just true. Once you start using the battery, then charges actually flow through the battery and the battery starts to heat up. If the battery starts to heat up, that means that some of that energy is being lost inside the battery. Remember that voltage is related to energy. So you're actually using some of the voltage here. So you actually don't get 3 volts out of your 3 volt battery if you actually turn something on. You may notice, you may not, I'll get to that in a second, you may notice that your EMF value, which is the ideal battery voltage, provided you don't actually turn it on and use it, the EMF should be, it really is higher than the actual voltage you get when you're using it. So if this is 3 volts, that might be 2.5 volts, the voltage difference from here. Why? Because you're losing, if this is 2.5 volts, you lost. You're not going to lose, but you used up half a volt in the circuit, mostly in the battery. So again, this, instead of going from 0 to 3, it might actually just go from 0 to 2.5 because some of the voltage was used up here. And then you have less voltage available in the circuit because some gets used up in the battery just to go through the battery itself. All right, you turn the thing off, and then suddenly it goes back up to 3 volts. Some of you may not notice that. You might see something where your EMF number is lower than the voltage when you're using it. You didn't do anything wrong. It's just something wrong with these things are miscalibrated. The truth is that when you turn on anything, you're going to get less voltage in reality through the circuit than when it's not. That's just true. So this funky looking symbol here, what is that, an epsilon or something, stands for EMF. It is that ideal voltage. But that's why we didn't plot this, because we actually turned the thing, we didn't use that number on the graph. We actually used the one up here, which is the voltage dropped over the resistor, measuring the energy usage over the resistor. That's the one that gets plotted on this graph. We'll trust that one, okay? So you collected voltage versus current. This is the voltage dropped over the resistor, the current going through the resistor, and I hope you notice that it is most definitely linear, okay? On Logger Pro, you want to do a best fit line. And I'm just going to make up a slope to keep life easy. Let's just say you got a slope of 0.1. You're going to get something like, you probably got 0.0 something, but it'd be 0.1 amps per volt, meaning that in my made up situation, if I had 0 volts, I'd get 0 current, 0 amps. If I had 1 volt of potential from the battery, if I had 1 volt, I would have had a current of 0.1 amps. If I had 2 volts, I would have had a current of 0.2 amps. If I had 3 volts, I would have had a current of 0.3 amps. So the greater potential I have here, that drives a greater current. And it's a linear relationship. That's what you should see. Now, if that's the case, the reciprocal of this is the resistance. The resistance, is going to be equal to 1 over your slope. So in my case right here, my resistance would be 1 over 0.1, which would be 10 ohms. That is the value of my resistor. So the resistance in ohms is the reciprocal of this. And again, notice that it's constant. Anything that has a linear relationship between current and voltage is said to be ohmic. It obeys Ohm's law. Ohm's law, written in its raw form, is a delta V. Some people just use a V. Whoops, you can't read that. Is delta V equals I times R, or R is actually the slope. It's just how it's typically written. Yeah, I guess in this case delta V equals R times I, but whatever, because R is the slope. That's the sorry, bad teacher. This would be I equals 1 over R times delta V, right? Because the slope is the reciprocal of the resistance. I'm going to erase this. So again, in this lab, current is your Y variable equals the slope, which is the reciprocal of the resistance, times the X variable, which is the voltage. You can see how that's related to Ohm's law. That's going to be your general equation. Because Ohm's law is written as delta V equals IR, we just have to multiply both sides by R. This is assuming that as you increase the current, as you increase the voltage, you increase the current, but the resistance stays constant. I do want to just say something about that. Now I have to check how I'm doing on time. I want to say a little something about that, because you know that as current increases, this is going to get hotter, the resistor and the wires. And so you also know from chapter 17 that when something gets hotter, its resistance goes up. There's that direct relationship between resistance and temperature. A good resistor is one whose resistance doesn't change much in terms as the temperature changes. A good resistor is one in which the resistance doesn't change much with temperature. So if that's the case, if it's linear, as this suggests, as we increase the voltage, we increase the current, but the resistance stays the same, we say it's ohmic. It's an ohmic material. This resistor is ohmic. For something where the resistance goes up with current, you're not going to get this linear relationship, and you wouldn't get a straight line here, and we would say that that is, as I wrote up here, non-ohmic. You should recognize what that is. As far as the math is concerned, for everything we do, we're going to limit it to ohmic relationships. So with the lab, be sure that it's a pretty simple lab to write up. If you're not sure what goes into the conclusion, which is explaining all this stuff and what the general equation is and how you know this, look on the Canvas page for lab notes and videos, and I talk about that, what goes into the conclusion. Again, it's pretty straightforward. Be sure you self-enroll in your lab group, which is Ohm's Law. I have it due this next Monday, whatever that is, the 23rd of March. Yeah, at 10 p.m. Again, if you're absent, just coordinate with the people that are in your typical lab group and just do the best you can. These are very unprecedented times. Please take care of yourself. You know that we really, really care about you. And I'll talk to you later.